Hello, Ariel. All right?
Yes.
Okay, so today we talk about graphs. What's graph? Graph is a data structure, right? With the vertex and the edges. Yeah. So the graph we usually represent the graph with G, and it's a set of what? A set of. Can you tell me? It's a set of V and E. What's V and E? Vertex.
And
Vertex, yeah. And what? Yeah, this is vertex, yeah. And what? That's the vertex. And what's this? What's this? What's this? What's this? The connections between the vertex. What do we call it? Start with E. E what? ED.
edges.
Yeah, edges. Well done. Yeah, vertex and edges. Okay. So this graph can be directional or bidirectional, yeah, or unidirectional. So it can be bidirectional. What does it mean bidirectional? Or directional, okay? Bidirectional or unidirectional, which is the same. Unidirectional or bidirectional. This is the same thing. And directional. What does it mean? Look, if it's directional, you can have this has error. 1 can go to 2, but 2 cannot go to 1. Okay? Right? That's directional.
Can I have 2 hours?
Yeah, if you want to go to 1, you have to put this here, right? Then bidirectional, it means you just put 1 can go to 2, 2 can go to 1. Okay? 2 can go to 3, 3 can go to 2. 3 can go to 4, 4 can go to 3. Okay, so this is the bidirectional. Okay, so if today's task is very simple, given a bidirectional or unidirectional graph, because it means that 1 can go to 2, 2 can go to 1, and something like 1, 2, 3, 4. So for example, this one, if I tell you, can you find the path between 1 to 4?
Yes.
Yeah, because it can go to 1 to 2, 2 to 4. Okay. How about there's a graph and a graph, yeah? Graph and 5 to 6 and then 7. Can you go from 3 to 7?
No.
Yeah, because look, this is a separate, right? There's no edges between these two components, yeah? Simple. Okay?
Easy.
So, easy, yeah. So you got this problem. So we are given these, so how, we are given this input, like 1 to 2, 2 to 3, 3 to 4, these edges, yeah? So how do we represent the graph? How do we represent a graph?
Like.
Do you still remember adjacent metric? Yeah.
1 can go to where we need.
Adjacent metric. So for example, like 1 to 2, 2 to 3. Okay, 2 to 3, 2 to 4. Okay.
Oh, yeah,
So how do we represent? How do we represent this? We can use the dictionary, yeah, key and the value. So how can we do this? The vertex, we call the vertex is the key. What's the vertex? 1, 2, 3, 4, yeah? 1, 2, 3, 4. And what's the value? This is vertex.
Vertex and
then this is the
value.
values. This is the key, yeah? And the values will be a list of the vertex. List of vertex. So 1 can go to 2, what?
1 can go to 2.
Well done. 2 can go to what?
1, 4, 3.
Yeah, 1, 4, 3, or 1, 3, 4, yeah. So a list of nodes it can go to. 3 can go to what?
2.
And 4 can go to what?
2.
Yeah, okay, so you see, this is the node dictionary, a hash map. Yeah, the keys are the nodes, the vertex. The values are list of the vertex that it can go to, okay?
All of them are 2 except one 2.
Yeah, so given this data structure, yeah, we already know how to build this adjacent matrix from the given edges, a list of edges, and how can we find out if there's a path between the target, the start to the finish, to the end? What can we do? What kind of algorithm can we use to traverse the graph? Traverse a tree. Tree is also a graph, yeah? Remember we talked about how do we travel a tree, remember? How many kind of algorithm are we doing? Breadth search, random, and depth search. This is the two we have learned so far, okay? So today we're going to use the breadth search. Yeah, of course, yeah, I'll show you later. 3 is also a graph, okay? Yeah,
Okay.
3 is also a graph. So breadth search can be also used to traverse the graph, okay? So if, for example, 1, I want to find out if 1 can go to 3, right? So I put the 1 in the queue, yeah? Remember the breadth search is the queue, yeah?
Yeah.
We put the queue 1 here. So we take 1 out. What's the kit of the 1? 1 can travel to 2, right?
2.
Okay, I put a 2 here. So I take a 2 out. Where can travel to?
1, 3, 4.
Okay, so do we need to visit the 1 again?
No.
No, because we already come from that. If we visit it, if we keep visiting 1, what happen?
Just read explanation, whatever that was.
It will never end, right?
Explanation.
Because look, I just come from 1, and if I take, I put a 2, and 2 and come to 1, and then it will be a cycle, right? You will do this forever, right? So we need what kind of data structure to remember the nodes we have visited. Hash set or notebook, yeah? We need to do this. This is a special
Actually, it's set.
hash set or set, yeah? Set, notebook, okay, set. Okay, so we can start from the nodes, and then we keep doing this breadth search until all the nodes has been searched, visited, right? And if we can't find the node, when we're expanding the nodes, if we can't find the finish, the end, then it returns false. Otherwise, if we visit it, and then we will return true. Okay, simple as that. Let's do this. Define that path exists. Path exists. So we given a star, and an end. And then we given a list of edges, yeah, edges. Okay, so first of all, we want to keep these edges is the list of the stuff to end, right? So we want to build a graph. So let's say graph equals default. Remember what's the key? Default dictionary.
.com.
What's the key? What key is the nodes and value is the list of the integer, right? Yeah? List of int, yeah?
Int.
Okay. So I think we also need do we need the n? No, we don't need the n. Okay.
What's n?
N is the number of edges, like 1, 2, 3. Okay, that's fine. Then we go through this for SE in edges, right? So look, GS dot append what? Append what? Look.
Edges.
Edges E, right? Remember this is bidimensional, so we also need a GE dot append what? GE dot append what? Append what? S, yes, we're done. Look, because S can go to E, it also means E can go to S, yeah? So I put it in the nodes, right? This is remember the value is the list of nodes it can go to from S, yeah? S can go to E, right? E can go to S, okay? So once we have this adjacent, this is called adjacent metric, right? Adjacent metric. Okay, adjacent metric. And then now I need to do what? Breadth search, right? So I have a queue. How do we implement a breadth search here? Using what kind of data structure?
DQ.
DQ. What's DQ mean?
Double-ended Q.
DQ. And then first of all, I need to put what in it?
Root.
Root.
Wait.
What?
Start.
Star or end, yeah? You can travel from the star or you can travel from the end. It's the same, right? You can start from the star or you can start from the finish, yeah? It doesn't matter, okay?
I like to start from the start.
Yeah, start. Okay. And now, remember, we need a hash set to remember the nodes we have seen, yeah? So scene equals what? What kind of data structure? Set, yeah, set. Set contains only the unique numbers, right? And then now how can we to travel this? Why what? Why what? Why what? Why we have something, right? Yeah, why we have something in the queue? Then we have to take a element from the queue, right? So we do what? What the pop left? What's the pop left? We want to take a queue, the front of the queue, front element of the queue. What? Huh? Let's go and see. C equals Q dot top left, yeah?
Yeah.
Let's call it the Q, yeah? The Q. We take the first element, look, we take a 1 out, and then what do we need to do?
We need to.
First of all, we need to find out if C has been visited before, right? The scene, yeah? If C in scene, continue, right? We have visited this, yeah? What does continue mean?
You just continue.
Continue to the next loop without going there. Continue means that continue to the next loop, yeah? Got it? Continue, okay? And if we put a break, what happens?
It'll stop.
Stop, you will jump to the after the loop, okay? That's the difference. Then, if at this point we haven't visited the C, so we want to mark it as visit. So how do we do this? Scene dot what? Add what?
C.
Add C, right down. And now I need to. Now this is we are at this C node. We want to expand all the nodes it can visit, right? So for I in graph C, right?
It's graph.
And then what do? We want to what?
Append.
Q dot append, yeah? That's right. Append I. Okay, so wait.
What's that? Oh yeah.
We haven't. So if C in C, so before that C here, we need to check if C equals n, right? Because we already if it is the end, what do we do? Return what?
True.
Return true because otherwise if this finish, what happen? What do we mean here? Return what? What does it mean? Return what?
False.
False. It means that all the nodes has been visited, but we can't find the end, right? So that's the breadth search, am I right? Yeah? Okay, does it make sense?
Yeah.
Okay. Okay, so I'm going to erase this bit. Okay, so can you write this? This is the most important part. Okay, so what do we do here? For what?
Something.
Yeah?
For
Yeah. For something, for what?
I.
Yeah, for I or anything like yeah. For in G what? GC. What does GC mean? What does GC mean?
It means.
What does GC mean? Come on. What does it mean? What's GC mean?
Graph.
Remember graph GC. What's GC mean? It means what's I? I is the nodes
Nice.
of what? C can what? What does this mean? GS upon E, GE upon S.
Oh, that it can go
From S to E or E to S.
Yeah.
So what does GC mean?
So I can go to C.
Yeah.
C.
All the nodes can. This is all the nodes C can go to, right?
Yeah.
And then we have nodes I. So what do we need to do?
Q dot.
Q dot append. Yeah. We want to push it into the queue. Remember, for the breadth search, we take the front of the queue, take the element from the front of queue, take it out, process it. Yeah. Check if it's the target element, which is the n. If not, if it's already visited, we continue. If not, we expand the nodes. We expand the nodes it can visit and put it append on the queue. Remember?
Yeah.
Yeah. Remember breadth search. What's breadth search?
Top to bottom.
Level by level. Look, if a tree is easy, yeah, level by level, but the graph is the same, yeah. If you look, if it's a graph, it's the same, yeah. It's the same. It's the same, right? Yeah. So you start from here. So what's next? It auto expand. It's here, right? And you take the tree here.
How about this one?
Yeah. And then the next one is you take this and expand its kit here. But you don't expand this one because this one has been visited before. But why we don't have this in the tree? Because in the tree you don't visit the parent again, right? Yeah. So we don't have that problem using the set. But in the graph you don't know if there's parent, right? Right. So we need to use this. Does it make sense?
Yeah.
What's the time complexity?
Oh.
Oh, n. What's n?
Oh yeah.
What's n?
No.
The number of nodes in the graph, in the vertex. What's the space complexity?
O, N,
Yeah, because we are using
D, Q, Q.
DQ and set. Yeah, and the graph here, graph. Yeah, lots of the space. Okay. Thank you. That's it. Good job. today.
Bye.